tell us a little bit about your Swiss background and why you became a cosmochemist.
Yeah. So I was born in Zurich, Switzerland, and I grew up in a suburb of Zurich and was always interested in nature and nature on Earth, but also nature in the outside of Earth. Our family, basically my father was a iron and steel engineer. He was a technical director of a US company in Zurich and helped develop and improve continuous casting. My mother was a linguist, but we spent most of our vacation and weekends in the Alps, hiking or skiing. And typically after dinner, we went for a walk. Sounds very simple, but that was an important element in the whole thing. On moonless nights, when there were no clouds, you could see the stars and the Milky Way very, very well, despite some light pollution. But I was really interested in that part of nature and wanted to learn more about it as a boy, and read children's books about astronomy. And later in high school, I checked out the school telescope, took it home and observed Jupiter and its moons, and wrote a science project about this. And then when I finished high school and started university, I started first studying astrophysics, but then switched to earth science, because with earth science I could combine my love for nature on Earth with nature outside of Earth. And this is how I got started. And then after I finished at ETH Zurich, I got an opportunity from my Ph.D. advisor. He offered me to study stardust, solid samples of stars, to learn more about our origins. And I jumped at that opportunity.
So the book of Genesis says, from dust we come, to dust we go, but you take it a step further and you say this is a specific kind of dust. So what exactly is stardust?
Yeah, stardust are solid samples of stars. And actually I have a few samples here. I'm going to pass around. There's a vial with liquid. It's just a water alcohol mixture. But what you should look at are the white particles suspended in this vial. And these are individual diamonds, and diamonds that didn't form on Earth, but they formed in space. They were condensates. They're condensates of the outflows of stars. So I passed this around. I just want to get it back afterwards. just kidding. Just kidding. Now they're everyone can take one grain, but they're so small you don't see them without a microscope. So these are really interesting because this is really these haven't changed since they formed before the start of the solar system. The solar system started about 4.5 billion years ago, and these minerals, these diamonds, are older than that, and they basically preserve the composition of the star from which these diamonds were made from. Mm. So this is stardust in this vial. It's the oldest material solid material that you can hold in your hand, that we have access to.
How do you go about finding stardust? You don't just run across it under your bed or whatever. How do you find stardust?
Yeah, this is really the most difficult part of the whole project, or of the whole thing. Stardust is very, very rare. Of a typical, unaltered meteorite, stardust is only every millionth particle is stardust. Only every millionth particle. So it's really a needle in a haystack problem. And we use the brute force approach to burn down the haystack to find a needle. And we don't burn down the rock, but we use acids to dissolve the rock and to dissolve minerals. And these are fragments of a meteorite that fell in Australia in 1969. I'll talk a little bit about this in my answer, but we use strong acids and a combination of different acid baths to extract that stardust, essentially burning down the haystack. And then we extract the acid-resistant minerals. That includes diamond, as in this vial, silicon carbide, sapphire, and many other types of minerals. And so this is where do we find these rocks that contain stardust? We have, I just opened up a cabinet and a drawer at the Field Museum in the South Loop. So that's a we have a lot of this particular meteorite in there. This is the Murchison meteorite. This is a meteorite that fell in Australia in 1969. So 1969 was a very special year for planetary science and cosmochemistry, obviously, because we had the first manned moon landing. And but in September, a few months after the moon landing, the Murchison meteorite fell in a rural area about 2 hours drive north of Melbourne, Australia. And it was a Sunday. People were, it's a small town. People were ready to go to church. And suddenly there was a bright fireball in the sky, loud sonic booms. And people thought an airplane is crashing. They were really panicking. Some of the citizens of Murchison saw planes coming down in the war, so they knew this reminded them of these instances. But then people recognized that it was a meteorite, a fireball, meteorite that broke up in the atmosphere and fell into the fields of Murchison. Some of the pieces fell onto a dairy farm and fell into like the cow manure, etc. So when I went to the 30-year anniversary of the Murchison fall to Murchison, I met a scientist who was actually at that time a student in 1969 and spent much of the day searching for pieces like this in the cow manure. And he still became a geologist, but he decided not to study meteorites after that experience. And that meteorite later that was acquired by the Field Museum in Chicago. It's about 100 kilograms fell. The Field Museum acquired almost half of it, thanks to the generous support of Chicago area donors who made money available to purchase that rock. It came to Chicago. And in 1987, a team at the University of Chicago discovered stardust by using these acid dissolution steps to find these exotic minerals with exotic compositions that came from stars. NASA tried another way. There's a NASA mission called Stardust that sampled dust from a comet in the solar system. At that time, scientists thought the comets were made out of stardust or had a high proportion of stardust, unaltered, because the comets, they orbit the sun far out in the outer solar system where they didn't get heated, and the primordial stardust is still there. This mission sampled the coma, the dust around the comet, brought it back to Earth in 2006. And I was a postdoc at that time, and I spent 2 years looking through this comet sample to look for stardust. I didn't find any. My colleague in St. Louis also spent 2 years. He found a few grains. But at hindsight, this mission shouldn't have be called Stardust. But we now know better. Murchison is the most prolific source of stardust, and has nothing to do with the cow manure, but it's a very well preserved and old meteorite. Yeah, so the stardust, the minerals in the stardust minerals, they haven't changed since they formed. They formed before 4.6 billion years. They are essentially time capsules, like time capsules. They formed from the elements that were made in their parent stars. They were incorporated, condensed as diamond in this case, and these carbon atoms in the diamond haven't changed, haven't moved much since they formed more than 4.6 billion years ago. These are the same parent stars that made the carbon in our body. So it's what makes stardust really interesting is that they haven't changed. The carbon in our body took up many forms. The food we eat, it was part of the food we eat. Part of it was CO2 in the atmosphere. But they have the same origin. If you want to learn about our origins, our parent stars, we can study stardust where the chemical fingerprints of the parent stars are still preserved. So this makes stardust really interesting. And the stars, why stars? Stars are the element factories of our universe. Almost all of the elements, except for hydrogen and some of the helium, were produced in stars. And the world around us, the atoms of the world around us was made in stars. To study our origins, we can study we can look at stardust with instruments and then find out what type of stars these atoms came from, and then even dive deeper and learn about the processes that happened in the stars, the nucleosynthetic processes that made these elements, the mixing processes that brought these elements to the surface and made them available for the universe, for our solar system later on.
There is a key Swiss element in your research with a very funny name. Tell us a little bit about that.
I think you're referring to the name of the mass spectrometer that we use at ETH Zurich. So the name of this mass spectrometer, which is a Swiss mass spectrometer, mass spectrometer is called Tom Dooley, and this was because it was named by its inventor, Dr. Harry Bauer, and his colleagues in Zurich. This mass spectrometer is so heavy that the initial lab floor didn't support it, so it had to be hanged from the ceiling, and they thought about a name. They always give names to these instruments, and they thought about an appropriate name. And they had this song going into their head. It's an Appalachian traditional ballad called Tom Dooley, and which became popular in 1958 by an American band. I forgot the name of it. It was a trio, but it's a murder ballad about the murderer Tom Dooley, who murdered his lover, and but it was popular in Switzerland as well, and they named the instrument for that. So it's kind of funny, but also sad in a way.
Dry Swiss humor.
Yeah, but it is Tom Dooley. When people in our community hear about it, they know this is a special instrument. This was finished. This instrument was built in 1999. Until today, it is the most sensitive instrument for helium and neon measurements, and it's the only instrument to date that can measure helium and neon in individual stardust grains. So it's a really important instrument. I made my Ph.D. thesis on this, and I still get access to it, so our projects still use that instrument.
What else can we learn from stardust?
Yeah, so besides finding out what type of stars it comes from, we can date stardust. We can find out how old it is. And this is where my group is really interested in. And stardust grains, once they condense and fly through space, they get exposed to cosmic rays, energetic particles in space, and new elements form in them. And what we do with Tom Dooley, we take these stardust grains and count the number of atoms produced by cosmic rays. And we know the production rate, so we can calculate how long they were in space. And that's interesting. You can find the oldest grains. This is great, of course, but what scientific questions can we address? We are looking for, when we do that for many different grains, we can look at the age distribution. We can see how the ages are distributed, and we are looking for clusters of ages. An age cluster typically means that these grains formed at the same time. These stardust grains form from stars. So that means these stars, the parent stars, formed at the same time. And in our data set, we found one age cluster. And we found a cluster, we found that many grains have formed from stars that formed around 7 billion years ago. So there was a time in our galaxy where about 2 times double the number of stars formed than normal. That is significant. And we looked into the astronomical literature and found that astronomers observed that too. They found that too independently. So we basically confirmed these astronomical observations with the stardust. So why suddenly more stars formed than normal? We don't know. But there are some ideas that we have, and that other people have.
What other big questions are still remaining?
Yeah, so obviously we just scratched the surface with about 50 ages. I mean, you can argue how good statistics you can do with 50 ages. Yeah. So we want to increase the number of ages, and we want to look for other age clusters. And astronomers observed with new satellites, they have indication that a satellite galaxy collided with our galaxy and provided fuel for star formation. That happened much earlier than the 7 billion years ago. And we want to find evidence for this in stardust. and maybe other age clusters that indicate galactic mergers. So I'm really interested in the big questions. What can Stardust tell us about our origins? What can we learn about our nature around us before the sun and the planets formed? About the history of our galaxy. And we can do that with the simple method of dating pre-solar grains. It just takes a lot of time to find them and then to analyze them, of course. But once we have more ages, we can learn more about the history of nature and our origins.
I just read that recently a meteor landed in a driveway in England. Can you make money with this stuff?
Yeah, I'm not allowed to talk about prices of meteorites. I have my boss here sitting, so I'm very careful with what I say. But yeah, meteorites they have a good price. I would say an average meteorite is probably around the price of gold. Meteorite like Murchison, it doesn't look like gold or spectacular, but it's actually scientifically extremely valuable, but also on the market. This is much more valuable than gold. Magnitude more valuable than gold. And without giving any numbers, Torsten. Yeah, you can make money. They are meteorite hunters, people who quit their ordinary jobs, who basically go when they hear about a meteorite fall, or they look at weather radar and they see a meteorite fall. They go there and try to find pieces and sell them. And they're so expensive that even the Field Museum cannot afford most of them. So we work with private collectors and donors who buy them for us or collect them for us and make them available to science. Mm-hmm. And some people make jewelry out of meteorites. There are Swiss watch companies who make watch faces with polished and etched meteorites. I've seen recently on the internet, not live, I've seen a BMW use the iron meteorite for its interior, right? I mean, this is special edition, of course. I don't drive it, don't worry. But so people are intrigued by the beauty and by of meteorites, and that makes them very attractive. And the prices of meteorites, they have risen, and I would say in the last 50 years, they have risen by a factor of 100. Wow. So good investment.
Definitely, yes. Yes. I would like to open the floor to the audience for some questions that you might have for Philipp.
Could I assume that everywhere where there has been a meteorite in the past, that this area is completely exhausted in looking for pieces of the meteorite? Like we have a place in Germany, in Nördlingen, which is still kind of visible that there was a meteorite whenever millions of years ago. But I suppose digging there would not bring you much results.
Yeah. So the question is, can you still find meteorites around here?
Or can you give us some address?
Yes.
Maybe that's it.
I mean, meteorites fall, on the order of kilograms and hundreds of kilograms. They fall pretty frequently, but they still fall mostly into the ocean and are not recovered. There are some chance recoveries, and usually people don't find them when they fall. But if they fall in the Chicago area, there was a fall in 2003 into the Chicago suburb of Park Forest. And people immediately went there and collected pieces. But a few years ago, I heard from some residents that they still found pieces. So yeah, usually they break up into small pieces, and most of the small pieces are not found, the big ones. With Nördlingen, with the Nördlinger Ries, that's a big impact crater in southern Germany. This was a much larger object, and it probably, like most of these larger objects, when they hit Earth, they evaporate, so nothing of the impactor is preserved typically. They mix with the target material. So, but good places to find meteorites are usually old surfaces. So one of the best places to find meteorites is the Atacama Desert in Chile. It's one of the oldest deserts on Earth, maybe the oldest desert on Earth, and there are meteorites that have been on that desert floor for more than 1 million years. And the other good places are northern Africa, the Sahara Desert, not as good as Atacama and Antarctica, because you have cold deserts there, and there are search parties from different countries which go every year to collect meteorites.
Coming back to the stardust, can the this stardust, if you study, can we find, or does this reveal, for example, some vegetable origin plant who can show us, for example, a way to know if there were some life? Maybe, I don't know where, of course, but can we have a clue studying the stardust?
So the stardust minerals that we look at, they are inorganic. So they're diamond, graphite, etc. They don't contain any organic compounds. But the meteorite like Murchison, they contain lots of organic and lots also pre-solar organics. So Murchison contains probably some precursor compounds of life. And meteorites fall, of course, today, but they fell throughout Earth's history, and they also fell before life arrived on Earth. And it is thought, based on the organic inventory of meteorites like Murchison, that these types of meteorites, which we called carbon-rich meteorites, carbonaceous chondrites, may have contributed some of the building blocks for life. And when I talk about organic compounds, they are amino acids in this meteorite, they are alcohols, sugars, etc. So lots of complexity. And
Professor
you can even
Dunant?
smell, you can open up the bottle. No, you don't smell it, but if it's in a Ziploc bag, it seals better. And when we open it up at the Field Museum, you can really smell the organic volatiles. They're still rich, even fell in 1969 and still degassing.
Professor Dunant?
So I think we've had one, maybe even two extrasolar visitors. Could you tell us more about those? The first one, long Hawaiian name, I can't remember. I think maybe the Scout or something like this, which might even be a chunk of hydrogen.
Yeah, so it is Oumuamua.
Oumuamua.
Right? And yeah, it is a really interesting object. And I guess based on the trajectory, it was determined that it's from outside of the solar system. And it left the solar system again. And there were not much time to do observations. And there were lots of interesting interpretations of these observations with different conclusions, and then as soon as one interpretation was published, there was the rebuttal published afterwards. So we are still not sure what it is. Clara, do you know more about this?
There was an idea that it was hydrogen. I think the latest one is maybe now it's carbon monoxide, CO. There's still a lot of active debate and several different conclusions that people are battling over.
So could we catch up with it, say in 10 or 15 years with enough time and enough delta V on a rocket?
No, but we can wait for other visitors to come.
Yeah, exactly. And this is, I think, and there was another one, as you mentioned, Boris Kino, and a comet. And if there were two, there must be more. So I think getting ready for those is interesting.
When we look at stardust and organic material, is contamination an issue or a challenge for you?
Yeah, that's an excellent question. Contamination is a big issue, especially with the organics. As soon as the meteorite lands on Earth, you have contamination from Earth. So I think ideally we want to have recover the meteorite immediately after it lands. And actually, 2019, in the spring before the pandemic started, there was a fall very similar to Murchison in Costa Rica, and the Aqua Sargas meteorite, and it was picked up almost immediately after it fell and put in apparently clean Ziploc bags. And we got the piece of it very quickly and put it in liquid nitrogen at the Field Museum. And we're still waiting for a grant proposal to get funded to analyze the hypervolatiles in that meteorite. And we think this is one of the least contaminated ones. But we can look for terrestrial contamination, and these meteorites are very porous, so you typically find them in the cracks on the surface, and you can look for like profiles, gradients that indicate contamination. You can also look at common compounds on Earth. You can look at isotopes, etc. But most meteorites have a substantial amount of contamination, and that needs to be subtracted from the inventory.
I'm interested also in the part of organic part of these sandust materials. How much overlap do you see in amino acids or building blocks of life of those materials with what we have on Earth? Is there a lot of overlap?
Yeah, I think there is a lot of overlap, and I think there are a lot of compounds that aren't found in life on Earth. So I'm not studying these currently, so I won't be able to give you the names. But yeah, there's a lot of diversity and a lot of overlap. One thing that comes to my mind when you ask me about the price of the meteorites, I think this will go up further. So it's really a good investment. But also, I mean, I read recently a paper by David, who proposed to use iron meteorites on the surface of Mars as building structures for future astronauts on the Martian surface, because you cannot just bring like large blocks of iron ore or steel from Earth. Every gram counts, and this was proposed to use them as building materials. But me, as a curator of meteorites, I said, okay, we want to preserve them for science. They're a valuable archive, so I want to make sure we have like I initially said 30 grams, but I revised it to 100 kilos, maybe per specimen. We should put aside for science at least. But maybe you want to comment on that.
We can do both.
So once this becomes really interesting, I believe the economic value will increase further.
We'll debate this over a glass of wine. But one more question?
It's amazing when you talk about 5, 6 billion years ago. That made me think about the relation between time and distance. I mean, and how precarious are our means today to really explore that the dimensions. What do you think that the basic question is, of course, about the organics in the meteorites, but the question is, there are signs of life as we know it, basic signs of life as we know it. So maybe presume that probably we're not alone. I mean, I'm convinced that we're not alone, but scientifically, it's difficult to prove that 5, 6 million years ago, those organic materials that were existing in a distance on time, which is, for me at least, I mean, difficult to measure or to imagine. Which is your assumption about this extraordinary, huge universe?
Yeah, it's an excellent point. I think just the fact that they're present in not only this meteorite, but in many other meteorites that predate, and many of these compounds predate the formation of the planets and the sun. And astronomers also observe them outside of the solar system with astronomical remote observations. These compounds are common. It's nothing really rare. So my personal opinion is that there's probably life elsewhere in the universe. It's very, very hard to find because of the large distances and the time it takes for signals to travel. So that's really, really hard. Also, the time span that intelligent life as we know it on Earth exists is really short. So that makes it really hard to find like a technological civilization, for example. So, but I have no doubt that they exist personally. also other life forms. In the solar system, it's probably harder, like the conditions may not be optimal for life as we know it, but there are several like candidates in the solar system that are being explored for potential sites of life, like Mars as a past site of life, or the satellites of Jupiter that have oceans, or satellites of Saturn. These could be all potential sites of life where we have life, may have life now. The big questions, obviously, is why are we here? That's something it's hard to answer, big philosophical questions. What we can address with Stardust is not so much is there life elsewhere in the universe, but one of the big questions we're interested in is, are we the result, this solar system as we know it, of a galactic collision that brought together the fuel for stars to form, to produce all these elements and later on compounds that we need? Or are we just a natural result of the stochastic evolution of our galaxy? I mean, these are questions that we can answer with Stardust. But your question about life is really, really interesting, and we can just get, we cannot answer it with that, obviously, but we can get informed elements to help answer that maybe in the future.
Thank you.
Well, thank you very much. I hope we can continue the conversation. We'll stop our taping here. We'll have a glass of wine.